In our last episode, we broke down the brain of the drone, the flight controller. Today, we're moving out to the muscles, the motors. These little cans decide how much thrust you've got, how efficient you are, and whether your build feels like a rocket or a school bus.
And if you're ever started to wonder what those little labels are on the side of the motor, like 2207 or 1750 kb, and wondering what it actually means, or you're trying to pick motors for a build and or your fleet, this episode is for you. We're decoding this information and the numbers and talking size, kV, efficiency, and how to match motors and props and the mission.
Yeah, so this is part two of our seven-part sUAS component series. If you haven't seen the flight controller breakdown, go check that out right after this episode. Welcome to the Swarm News, where the veterans and engineers talk about defensive tech the way it actually works, not the way it looks in a briefing. I'm Joshua Hill, and with our weekly update is my co-host.
And I'm Vincent Lewis. And thanks, Josh. Before we get started in this episode, we're going to go over a little bit of the news that's going on that everyone probably want to know. And all right, let's get into what's going on in the sUAS news and DoD industry for drones. Three big moves are happening recently with the counter sUAS nerve center at the Pentagon. They have Replicator 2 finally buying hardware and a major unlock on the blue sUAS list. And what matters basically what's going to end up happening with those situations. And for every OEM listed part that goes on those drones. So on the first one, we're going to talk about the defense industry, or FY26 defense bill quietly has been enacted to where something huge for counter U.S. operations, pretty much progress through to where Congress created a new joint interagency task force 101. We talked about it a little bit in the past, and it wrote it into Title 10 as the central coordinator for all DoD counter sUAS efforts. This director reports straight to the Deputy Secretary of Defense. They'll interpret what's going on for what the services need, what their authorities will be, how they will handle and include information to both DoD, the Pentagon, and other entities who need to know, and facilitating what they need to do for their facilities and the assets that they cover for protection. Basically, in the next 6 months, they'll be given a brief on what they'll be doing for updates. And for all you flying or building drones near critical infrastructure, this is a policy for the decisions that are going on with what will and can be allowed and how they'll defeat these different aircraft. So if you're wanting to know any of this information to either capitalize on the civilian side as a entrepreneur, this may be an opportunity you want to look into to see what's going on. And if you're an avid flyer who does flights close to it, this is your time to know you need to stop. If you haven't already, you should be anyway. But this framework will give you insight to understanding the changes that will be coming in the future for DoD, how DOJ will write this into the playbook for how lawfully the DoD will be able to interact with taking down sUAS and making it to where it's more simpler and quicker versus how this old bureaucracy of you can't knock down an aircraft because it's a terrorist thing that's going out the window. So with this new director coming in and Task Force 401 being put in place, this will now implement systems and legislation and rules that allow everybody know what the heck's going on and to protect our infrastructure in the United States. For the second one we have, which is the Replicator 2, is no longer just a slide deck. Since the JIATF 401 has been announced, the first replicator process for purchase has been put into place also. Two Drone Hunter F700 counter UAS systems scheduled for delivery this spring will help to defend U.S. installations against small sUAS. So they have finally got something in place to be able to taking care of those aircraft. Replicator as well is DoD's first lane for fielding large numbers of new capabilities. Between phase one, they were going to push thousands of autonomous platforms basically to see which one's best, and then they're going to work with phase two, which the JIATIF for one will lead how to stop sUAS using sensors, tracking them, and taking them out before they can actually become a threat to both people and critical infrastructure. And if you're building sensors, AI-based detection efforts, Replicator 2 is now in a place to where a real ramp up for programs that are needed will be able to be not just a buzzword, but something that can be used that you can look up and know you have an opportunity to provide a service to the DoD now and quickly. And then for manufacturers, DIU has officially opened up the blue sUAS or UAS cleared list by recognizing AUVSI's green UAS certification as a direct pathway if your platform passes green UAS. So basically, if it's a system that is made and from here, so if you make it to that list and it works, then you will be able to be on there. And it can now be added to the blue sUAS or UAS cleared list without going through a whole separate, smaller, slower DIU process. So if you already are incorporated into the AUVSI's program, you can pretty much automatically get put onto the DIU process of being accepted into a DoD vendor or provider. Then DIU and AUSVI or AUVSI have also built a small cadre of recognized third-party assessors, names like MTSI, AUSVI itself, and Dark Wolf Solutions, to run the cyber and supply chain reviews. The idea is to spread or speed up the throughput and give more US and allied sUAS companies a realistic timeline to become trusted options for federal and DoD buyers, which is a significant help for companies and or agencies and even the different branches of the military to get systems quicker. If you are new to this is pretty much one of those things that'll help you understand what's going on in that realm. And we want to try to provide that information so that you're understanding what's going on. And we want to help build out the industry and getting the knowledge out. So we also appreciate all those who've liked and subscribed to our channels and actually like to learn more what we got going on. So if you like what we provide and what our services are for giving information and understanding for the whole gambit of the sUAS realm, we'd like to ask that you like, subscribe, and follow us going forward. With that being said, you got anything to add on there or anything more, Josh?
No, man, I think that was a good amount of info that you passed. So let's go ahead and get into it. Yeah. Let's zoom back out to the big picture here. In the system architecture of small UAS, where do the motors fit?
So typically motors are the muscle. The flight controller decides what needs to be done or how they need to function and how it happens. And the ESCs translate that into electrical current. The motors turn electrical energy into a mechanical thrust through the propellers themselves.
Okay, so when I punch the throttle or I bank real hard, what's actually happening between my fingers and the motors?
So what you get is that your stick input goes into the radio for the motors to either go up or down as needed in order to get that motor to do what's needed to get it referenced the right direction.
Okay, and I mean, this isn't slow. I mean, we're talking milliseconds.
Yeah, this is pretty much in real time. When you think about it, the modern systems update hundreds of thousands of times per second, and the motors are consistently making micro adjustments to keep the aircraft stable and responsive.
So, all right, let's decode the side of the can, right? So a 22071750 kV. What is that actually telling me?
So to be honest, this basically is the first part is 2207 is the size. 22 is the stator diameter or the inside of the motor. This is what the bell or the outside of the motor is rotating around. And that's in the aspect of it is the millimeter size of the stator in general. Then you have 07, which is the stator height, which is the actual height of the motor, real quick, so you can see. So when you take it into consideration with this as an example, right? So you have, this is the bell. Inside those little silver is, that's the stator. So it's talking about that intersection of it, and then which is the height of the stator itself. So when you're looking at a motor, it's talking about the height and the size of the stator in there. Then you have other parts like this, the bell, which sits over top of the stators, which is attaching the motor or the prop to the motor itself. And then the bigger the diameter basically is the taller the stator and how many copper or iron windings are in there, which usually means more torque and thrust, potentially.
Okay, so let's talk about 2306 versus a 2207. What's the real world difference here with those?
Just basically, it's a slightly larger diameter or shorter height. So basically, think of it as the stator itself is bigger, but the height is shorter. So it's a little bit more scrunched down, but spread out so that they get the
Okay.
windings a little bit spread out. And basically, whereas 2207 is narrower but taller, and this changes the torque delivery and how it feels with different props. So for 5-inch freestyle, 2207 or 2306 is your sweet spot for your motors. So like for this one, if I'm not mistaken, this one is 22 millimeters around at 4 millimeters height. So it's a pretty small motor compared to others. Is like this one that we have for one of my 7-inch builds is, I don't have it on here, but I have to look at it, but you can tell significant difference in height versus how it's built. So it just dictates your sizes.
So let's move on to the kV. A 1750 kV versus a 2450 kV. What do those numbers actually mean?
So kV is RPM with no load. So a 1750 kV motor on 6S has a theoretical no load RPM of 1750. You never hit that under a load, but it always lets you compare your motor speed. So it allows you to kind of understand what you need and what you can possibly put into it. So the higher kV, the more RPMs per volt. The lower the kV, the less RPMs, usually for more torque and more efficiency, basically.
Okay, so what happens when someone slaps a high kV motor on a high voltage pack?
So what'll happen is you draw a massive amount of current, you run hot, and then after that, you're going to pretty much stress out your ESCs and your batteries, which you could pretty much blow the battery and or blow ESCs if it's drawing way too much than what it needs. Because when we get into ESCs, I'll explain a little bit more, but you don't want to overamp your ESCs, because as soon as you put too much voltage into it, or better example, your 3040, the 3040 ESCs that I have from Castle are basically 30 amps consistent with 40 amps in burst, which means that for a specific amount of time, it can go up to 40 amps, but you don't want to go over that, because after you go over it too long, it puts too much voltage in, which will heat it up and will blow the MOSFETs and other components inside the ESC. So you don't want to put it in too much voltage.
Okay, so what's a good rule of thumb to go with then?
Think of it in like triangle: kV, prop size, and voltage. All in this aspect will help you to build out what you need for a spec for what you're trying to build. So if props get bigger or voltage goes up, kV should usually come down. So when you're building out your motor and your ESCs to meet the amount of thrust you need. So like in this case, I have a 7-inch prop with a small motor. I'm going to say it's 2207 or 2407 motor. So basically this motor is built to go with the 60 amp ESC, so I can be able to draw the most efficient thrust that I need with the prop and this without actually overloading it with too much power. So you want to keep it at a place to where your motors max out with whatever weight you're trying to pick out. So if you need, say you're carrying 20 pounds worth of weight, you want your motor and ESC to be able to push out at least 10% to 20% more if possible of thrust, so that you can put on the thrust you need to be able to function normally.
Okay, so if two motors can look identical but perform completely different, what actually matters on the inside of the motors?
So if you go into the inside of it, like I was showing earlier, the stator and lamination and windings make a big difference. So basically the type of wiring that's in that motor helps out with making a determination on what you pick. So like you'll hear something oxygen-free copper. What it is that the oxygen-free is a laminated copper that's been rolled to where it didn't get a chance to really start to build up any oxidation on it. So you'll get a better flow of electricity through the wires, or they've been laminated as they've been put on so that the flow of electricity will go at the most highest peak that it possibly can into it. And when you look at the bell is what the size of your magnet. So the taller the bell means the bigger size of the magnet, which means that more force can also be put into it. So those are things you're kind of looking at, along with your bearings and what kind of bearings are going into it. So if you're looking at specifics in some Japanese like bearings, they're pretty well built matte bearings and they flow well. So you don't have to worry about them binding up or having problems, because when you spin the motor, sometimes you can feel how free it will flow. Like some motors, even with magnets on it, can flow. You spin it and it'll just keep going and it flows well because of the bearings in there. Some motors also have two bearings in it, where instead of one in the bottom and in the top, typically you have about two in it. So one in the top and the bottom, that helps it. And those bearings help to drive the motor smoothly. The stators with the right insides can actually make it work well because you get more electricity through and quicker in and out. The magnets, depending on what you're using for the magnets, also help to drive your force you're getting around.
Okay. So the bearings to me sound like they're for helping with efficiency.
Correct. It's more of a help with supporting building a flow of the motor without having to have a whole lot of resistance on it, and the prop to be able to spin well.
Okay. And what about the magnets and the bell construction? Like what thought process goes into that?
The stronger the magnet, the more rigid the bells will be, and then it helps maintain torque and consistency at the higher RPMs. If magnets, basically shift or the bells flexes, you're going to get a lot more vibration. The more vibration you get into the system means the less efficient the aircraft will fly, and it brings back into the flight controller, and the flight controller will recognize that vibration as it's flying, which means you have to do more tuning.
So fleet guys versus hobby builders, how much should you pay for quality?
So someone's building a fleet means you're 9 times out of 10 either selling or using it for service. So you're going to put more time into it and having a better quality aircraft. So you want to have more of a system that has better built motors and ESCs than you would for just someone who just want to build aircraft. You just want to get something built and flying. You don't have to spend an arm and a leg. You just get what you need to get it built, but you don't want to be too cheap either, because I've had motors that I bought that were like tiny, paid $10 for them, and they lasted me like 2 flights and they broke literally because the stator, the bearing and the rod that was in it that held the motor together, it snapped after flights and it didn't help. So you don't want to go too cheap, but sometimes you may get lucky and you find some that actually work well. But in general rule of thumb, if you're flying for yourself and you only built one, you can go as cheap as you need to get started. But if you're doing a fleet, you don't want to go cheap. You want to go with whatever you need that's going to be an in-between to meet the quality without having to have a higher expense, so you can be able to make a profit off of it.
Okay. So let's make this actionable now. How do you match motors to props to voltage in the mission? How do we do that?
So if you take like the frame size, such as a 3-inch cinema whoop or a 5-inch freestyle or a 7-inch long range drone or just anything like that, each operates in different thrust and efficiencies. So you're going to have to figure out which one is the aircraft you're wanting to build.
Okay. So why don't you walk us through a common build then? Like, give us an example.
So in a standard, like say 5-inch freestyle frame, with what you want to typically build it out of is probably a 6S. It's the most common now. It used to be 4S was the big thing back about almost 10 years ago. 4S was like a common, very inexpensive build. And then they start realizing like I can get more speed and more power if I go up in battery size, which there is no in between. Well, I can't say there isn't, but there is very less likely to find a 5S battery. So 4S, the next step up was 6S. But the problem is that at the time when they were first kind of becoming big, there wasn't a motor to meet up with the 6S. So you had to use 4S type motors to meet the 6S batteries. Then the motor started to come out, where that's what this is the big difference of. So if you're building a 5-inch freestyle 6S frame, you're going to want something like a 2207 or 2306 type motor with at least between 1700 to 1900 kV range. Whereas for the 7-inch long range, you're still going to be at a 6S battery with a little lower kV though. You're going to be sitting at like between 13 and 1500 kV for more torque, so you can get more power to push what you're needing to pick up. Then for like a cinema whoop, you can go up to like 22,000 or kV on that, which you can be up high, 18, 12. I've seen them to as big as like 22,000 kV. So the smaller the aircraft, you can go with a higher kV. The bigger the aircraft, you want to kind of go lower. You're typically always going to go lower in the kV.
And so how does all of this tie into the ESC selection?
So basically, that's where I was saying earlier with the motor, prop, and your ESC, you need to figure out what the combination works well. I found that like T-Motor did a very good job of explaining, for if you're looking for something, you can go in there and find the specs for their props, their motors, and their ESCs, so you know how much thrust you're going to get. So say in this case, a prop, the motor and ESC together all produced a 10, let's go with a hypothetical 10 pounds of thrust. So now you times that times 4 arms. Now you got 40 pounds of thrust that you can pretty much utilize to pick up whatever. And that's that. And you want to do it off of a percentage of at 75%, not 100, because you needed the extra percentage of thrust. Now if you're topped out at say 70 at 100% at 40, that means that if you're trying to pick up 40, you're not going to get it. So you always want to go between 75, 60% max of your thrust. So you're going to have to calculate at what percentage will you get that much thrust out of. And you can get those off of typically manufacturers of this motor with this ESC or this type of amperage coming in with this prop will produce this amount of thrust. And that's how you start to build out what you want in regards to your motors and ESC combos. And then you have pitch that will go into the prop. And that's where that one gets a little complicated. It goes into massive aerodynamics. And it's a whole nother story. But your pitch and your blade also gets a change in how much you can pick up, because depending on how big it is means more thrust can be reduced. And the pitch on it determines how much of authority it will put in to do that. So then in overall, without upgrading your SCs or inviting any other things into it, this is keeping you from running into worrying about situations where you have brownouts or having to worry about magic smoke coming out.
Okay. So if someone wants flight time over raw power, what are we doing and changing?
So you want to lower your KV first, go with a motor that doesn't have a high KV level, that has a very efficient prop to go with it, and then a cruise speed in the mid throttle range of efficiency zone. So you want to make it to where your throttle is not having to be maxed out. You need to make sure that whatever you're selecting is there. And there's a couple of apps, and we'll add those in that you can get those to figure out what would be the best when you have a combination of the motor, ESC, and prop together.
Okay. And what about commercial operators? What should they be looking for?
Honestly, they should be optimizing it for prioritizing their time or runtime, the temperature stability, because they're going to probably be running more often, and they're going to be running between high temperatures in the summer and then lower temperatures in the winter. So their aircraft has to be able to be efficient at all ranges. So they're needing to figure out what their runtime needs to be at an optimized range between, say, 70 degrees to about 40 degrees operationally, so that they know that in those ranges that aircraft can be able to function where it needs to be. And that's a general range. You may be, depending on where you are, it could be hotter. So like when we were down in Huntsville, the temperatures were way hotter. So our batteries were getting burnt real quick because it was just burning out a lot of the temp. But you also have to be considerate of that causing other problems with the system. If it gets too hot, it could blow and then ends up causing your catastrophic failure in the whole system. So not just, how hard you punch it. Basically, you don't need it to have it to where if you're functioning, you need to get the power through with being able to punch it, but not having it to where if you punch it for too long, it burns it out. But at the same time, knowing that your temperatures can help you support it, like in the cold, it'll be able to fly longer, if that makes sense. I'll clarify that a little later.
Okay. So let's talk about like mistakes. Like what are some of the biggest mistakes that we should be looking for?
So some of the things that people do is that they just buy a motor. They see something like, say, oh, I think this prop will work with this motor, and I can just go get any old ESC and just throw them together and put it on. That's you I guess going into where you don't have to go into doing a lot of research. I was saying earlier, this is where we're about to go into where you don't want to just punch the throttle, which is what we call when you throw the throttle from 0 to 100 and you get it up because you just need it, or you just need the thrust. If you just put together a motor, a prop, and ESC without doing at least a little bit of research on what it would be with all that together, that's where you burn out an ESC, is because this prop may not be able to be functionally, it could work together and they go to well for a minute, but as soon as you need it to push some power, this may draw too much power off that ESC and blow it. So you do need to know at least a little bit about what you're looking for before you actually put some things together.
Okay. What's the second biggest issue?
Don't underestimate your weight, because you may know that at the time when you're building it that, oh, well, my overall for the components that I have everything together is basically weighing 5 pounds, and my thrust is able to pick up 6 pounds. But then you just say, oh, I want to put a camera on and I want to put this, and you add on a couple other little things. Now you're at 6 pounds and you're literally at your limits of what your weight. So you want to try to keep your weight below the amount that you actually are building for. So if you have 7 pounds that can be picked up, you want to try to build it under, if you can, at 5 pounds or even 6 pounds if you need to, but you give yourself a little bit of wiggle room in case you need it. So if you need to change the battery, because things happen where the batteries you get will not be the battery you can get later on. So
Okay.
constantly being able to adjust as you need.
And what's the last thing that we should be like focused on?
When you can buy it at a reasonable price, do it. But if you're building it for a customer, as anything, most people know, don't buy it as cheap. Find the middle of the road motor. Get some motors if you think that they are cheap. Get them and test them. Verify that they work and they'll do what you need to. It'll save you money in the long run because you'll know what you're getting, and then you'll know also what will happen over time. And it also save you embarrassment if you're, say, sending it to your customer and they get 2 flights in and it burns out because you bought something super cheap and you didn't test it prior. And then on the aspect of for hobbyists, if you do buy it cheap, just know you pay for what you buy. Get what you need, but make sure you do the data understanding. And you may want to look at it as, you are adding a QC into your own build. So, and if you don't know what QC, quality check. So you're doing your own quality checks because you're the builder. And any of these issues can cause a lot of headaches. And I'll put it like this: vibration from the motors can cause you more problems than you realize. And that could cause you a headache trying to figure out what to do.
Okay. So let's talk about troubleshooting since you just talked about QC and issues. What are some like signs and signals that we should be looking for with troubleshooting?
One, really hot motors. When you can feel the motor getting hot, that means there's a lot of current being drawn through it. So you want to figure out what you're doing with, one, what's going on. Two, your ESCs need to be at a place to where they can be cool because they're the ones that are drawing that power through also. So if they're drawing all the power and they're not getting cool, I've seen it where I'm like, this should be working. And I've had an ESC that was sitting in a tube, and go figure, I didn't realize that ESC being in a tube, not getting just the air flowing over from the props, all it needed was that it would cool it down and keep it going. So you want to make sure that you have a good flying aircraft. You have vibrations, you're cued to inspect your bearings, inspect the balance and your connections. And a lot of times we'll talk a little bit more on the props, I think, at a different time, but there at some like regular airplanes, like actual fixed wing aircraft, you want to have balanced props too, because these props typically come from the manufacturer. Well, that's one good thing. These come balanced, but if you have a 2-blade prop, you can get a balancing tool and figure out if it's balanced, because that vibration, like I said, can cause you a lot of headache in the long run.
Okay. So we've covered the muscle. What's
the next one is going to be the ESCs and how it translates to the flight controller and the motors, their protocols and current ratings, and how not to make them fuse into basically your system, basically becoming a big block and burning up and letting out what we call the magic smoke, which a lot of people will probably understand that more after this. But that magic smoke coming out is not what you want. So
Yeah.
in that.
So we'd like to interact with our subscribers and our followers. So drop a comment on what you're using for motors to fly your craft. Are you using the 2207 freestyle? Are you using a 28 something long range, something custom? Let us know.
Yeah, and if this helps you in your build to be smarter in what you're doing, please like, subscribe, and share with other builders in your group or people that you know that may think this is helpful to them. So yeah, thank you. Appreciate you for
thank you for watching the Swarm News, guys. Yeah, we'll see you at the next one.
Yep, take care.